Si è rotto. Pigro. Un po' super gesto.
Il girello più che altro.
Vediamo, che dici? Troppo pochi? (901) Bargiacchi. Lei era dottorata in tutela, in pratica, in Senato, so che non l'ho mai vista questa ragazza, no? E la Francesca Civano alla fine si... Sì, perché diciamo, lei... Ma non la fa perché... Tipo le gomite che fa contatto col piede, le nostre così non ce la faccio.
Diciamo che non sembra che abbia mai avuto una gran voglia di vedere.
Però uno lo dice subito, non lascia le cose così. Sì, funziona. Eccoci. Please have a seat so we can start this morning session. So welcome back everybody after the social dinner and the football match. There's session this morning will be a review by Roberto.
Thanks. Good morning, everybody. Thanks a lot to the organizer for inviting me for this review talk. Logistically fast and present you a lot of work. And study the early black hole population in the early universe. As far as I'm concerned, there's a lot of people that have been very honored to work. And the year was 2000, and as you can see, it was the discovery of the first quasar, redshift 5. Outdated, but basically you see we know now some 400 quasars and 7.5. This is how a typical quasar at redshift 7.5 look, and you see that basically it's completely in the near infrared. Now, if you're typically to help you out, this is a timeline, linear timeline of the cosmic time from the universe till part where it's called the Dark Ages, and then on the right, it's the universe with galaxies. That's the distinction between Dark Ages and not. And basically, the quasars we know so far populate this part. And the idea is to increase this distribution and push it as far to the left as we can. One of the first important discoveries, and surprise perhaps, was the realization that the rest frame UV spectrum of this quasar look very similar to what we see in the typical quasar in the Sloan catalogs or even lower redshift. This is a comparison from Mortlock et al. Between the spectrum of a redshift 7 quasar in black and the template based on the SED quasar redshift 2, and you see that basically it's a very close match. Now, with time, we secured increasingly big and sensitive data sets, and one of the best ones that are currently available is this one from Valentina Dodorico's program, the XQR30, where they secured some very sensitive signal to noise is no longer the limit. And tomorrow, I think Manuela will present this work that, with this amazing data quality, impact of outflows compared to the typical population of redshift 2 quasars. I think one of the most striking results, especially because I really saw it happening in the last few years, was the fact that we started to secure measurements of the neutral fraction of the gas in the IgM in different cosmic times. Only a few years ago, that's what ionized, and then suddenly when you start to get samples at redshift 7 and so on, you start to measure neutral gas fraction that are substantial, 0.3, 0.5, 0.7. So you really see that in a short time scale, you Of course, the black hole mass is one of the obvious things we learn from the quasar spectrum. Typically, the argument is the virial argument applied to the Broglie regions, and this is, again, in the same x-axis. Now I'm showing here the distribution in black hole mass. This is the current picture, and as the title of the slide suggests, there is a growth problem. This has been already hinted to, I think, Tuesday. Basically, the idea is that if the black hole grows at the Eddington rate, the growth is exponential, and basically you have an unfolding time that's the salpeter time is 45 mega-years, depending on basically the accretion rate, the Eddington accretion rate, and radiative efficiency. And basically, with this assumption, you can trace back how big was the black hole throughout its accretion history, and you see immediately two things. First of all, a relatively massive black hole, a 10 to the 9 black hole at redshift 7.5, is more interesting than an overwhelmingly large black hole at redshift 6 because of the exponential growth. The second thing is that if you go back to, let's say, redshift 15, where you assume, okay, first galaxies start to form, you already see that the black holes need to be some 10 to the 5 solar masses, so they must be relatively massive. And even if you push it to really back in time, back to the Big Bang, you end up with a seed that has to be some 100 solar suggested, and some have been discussed in the last few days here. One, of course, is to have heavy seeds with black hole masses of 10 to the 4, 10 to the 6. The Eddington, times, and then you can basically grow the black hole more and more. And the other point is basically that you push back in time as much as you can, and basically assume that these black holes form primordially. Of course, it would be nice to push the redshift frontier further and further to get better constraints, but this is going to be extreme. And for a move from redshift 6 to redshift 9, you drop by 4 orders of magnitude. So it's very difficult. The universe doesn't have halos that are massive enough to form the quasars. And of course, this you would need a very high, very wide area in the near infrared, very sensitive, and this is one of the expectations for you. Study the quasar. It's not just nice to discover new quasars, but we want to understand them. So we started to do, we as a community started to do a number of follow-up, and obviously radio follow-up was one of the first ones. And now we have, we start to have a sample of a radio loud quasar detected at redshift larger than 5 or so. This is a compilation from a recent paper by Bagnados and collaborators. We also detected some radio-quiet quasars, and Quirin on Monday showed the case of 1030, which is probably the most radio-quiet quasar known so far at the redshift larger than 6, and that has been detected with their sensitive VLA observations. Sylvia probably later will talk about this discovery of the first blazar observed at redshift larger than 6. Here you see the SED, and here is the optical image, and the overlap is the radio contours. And of course, it's not only radio, we have X-rays. This is a compilation from a recent paper by Fabio, where you see that we start to have sizable samples of quasars that have been observed in the X-rays and have been detected, including one that was detected famously with the Rosita, sorry. And of course, using all this X-ray observation, you can do all the studies of the accretion and the phenomenology of GN, and Guido and Elisabetta use this information to challenge the cosmological paradigm up to very, very high redshift. Now, that was it for the quasar, but the black hole doesn't, the black holes don't reside in the void. They are typically in a galaxy, and we would like to understand these galaxies. This has been tried with the HST. I had papers with that, but a lot of other people tried, and we all failed. Really, it was a disaster, and this is the reason. The contrast here, it's very unfavorable. The reddest bands you can target with the HST still cover the rest frame UV of the quasar at this redshift. So basically, you end up with the noise maps like this once you remove the PSF of the quasar. The big hope is to get to manage to do this with James Webb, but it won't be trivial. This is a warning, because it might be, and we'll see later, that some sources are very compact, and if the quasarous galaxy is very compact, you're still fighting against the PSF of the quasar to get some information. Of course, in the meantime, we can focus on the other part of the spectrum and go to the rest frame far infrared that can now be probed with ALMA and other millimeter facilities. Antonio on Monday presented this work where he compiled the 6, and then with some modeling, you can get parameters like the temperature of the dust, the mass of with sufficient depth, turn out to have dust masses of 10 to the 8. These are big, and again, we are talking about and even if you account for you ignore the reverse shock from supernovae, you will have from the 10 to the 9, 10 to the 10 solar masses. Lines. Antonio presented this work on the underwater. Something about the physics of the ISM that produces this line, like the density, the excitation temperature, the kind of mechanism. It's not just detections, though. You have also maps, in particular in this case for the C+ line, which is the brightest far-infrared line for basically any galaxy. And in this work by Neeleman and collaborators, they characterize the size of the C+ versus the dust. So basically you think in terms of gas versus dust. And you see that basically the gas is always more extended than the dust. And then I color-coded this based on the kind of kinematical information they have. And they see that basically a third of the sample is dominated by rotation, a third is dominated by dispersion, and a third shows disturbed morphology and kinematics. And interestingly enough, the are two highlights that we observed then with really high resolution. This quasar is called J0005 and has been observed with ALMA at 400 parsec resolution. It's really stunning that we can get this kind of details for sources at redshift 6.6 in this case. You see here the dust continuum map, the C+ map, and this show this kind of sort of spiral arm, single spiral arm that is clearly revealing there's some interaction with the companion. The velocity field has a gradient that is suggestive of rotation, but there are also some obvious non-rotational components. And then this other case here has been observed down to 200 parsec resolution. This is one of the most compact sources we found. And you really see that the data quality is amazing, but the map is not as impressive. I mean, it's kind of a point source. In the dust, it's basically a point source almost. Which, okay, it's a bit depressing for PR reasons, but it's extremely exciting for the science that it implies. You clearly see it has been resolved. We have a clear rotation pattern in this case. But just to appreciate how compact are these or how small in angular scales are these sources, I compare them, I try to scale them with a local AGN, just a poll who recognizes this source here. Anyone? Louder? It's Markarian 231. And you see it's, I mean, they are very compact. It's undeniable. So one of the reasons why, when we designed this program, we were hoping to resolve the sphere of influence and get a dynamical mass of the black hole the same way that Federico presented on Monday for the Wisdom project. Unfortunately, we failed. There's no indication whatsoever that the black hole has an imprint on the dynamical of the gas in this source. And the reason is not that we didn't see the sphere of influence. Here I'm showing the sphere of influence as a function of redshift. These are the sources studied in the local universe, and this is, you see, we should have resolved it. And but the problem is that in the central beam, we still have some 10 to the 10 solar masses in gas. So the dynamic of the system there is completely dominated by the gas reservoir and not really the black hole. The black hole is just 10% of that, which was surprising, a bit depressing for us observers, but was not completely surprising for our theoretician friends that really predict that the host galaxy of this quasar, this is a simulation by Alessandro Lupi collaborators seen here in the molecular gas reservoir and expected luminosity in far infrared and C+. They really expect these sources to be extremely compact. The scale here, the bar is 4 kiloparsecs. So they really, it wasn't surprising for them to see that these sources are really compact. Not all of them are so compact, though. This is an example from a paper I wrote a few years ago, where we discovered this system, it's a quasarous galaxy here, with this elongated structure. This is a companion source, this possibly another companion or just a tail of the host galaxy. And we interpret it as the tidal stripping of a satellite galaxies that is passing close to the pericenter in its orbit around the black hole, the quasarous galaxy. The fact that there are companion sources around this high-redshift quasar is not surprising. Actually, this is the answer of all the formation models. You need to put the black holes in this is a plot of capturing this from companions. This the excess of galaxies found around quasars as a function of the separation from the quasar, from a paper by Romain Meyer and collaborators. And you see here basically in orange and blue the contribution from ALMA and Muse respectively in detecting companion sources around these quasars. At larger scales, the most prominent example is 1030 again. If it's not your first AGN meeting here, you must have heard this from Roberto or Marco. We were with a long campaign with multiple instruments and tens of hours of integration with mods and other instruments. They managed to secure the redshift of a number of sources and prove the quasar, and they're showing an excess compared to what you would expect based on their selection function for a general field. And the nebula of hydrogen that is surrounding these galaxies perhaps is the source that I showed you before, the merger. The orange spectacular example is this one, which not surprisingly perhaps is the source that I showed you before, the merger. Just one side of the system with Muse. You really see this extended emission of gas, all enveloping only just one side of the system. The James Webb data that we secured with a dedicated program will do near the James Webb data that we secured with a dedicated program will do near-spec IQ observations of the system with 2 pointings. So we will complete map both the quasar and the companions and the Lyman alpha halo. And test, for instance, if this Lyman alpha halo is enriched with gas, with metals or not, if it's pristine gas falling in or outflows and so on. So it's going to be really exciting. So I'll wrap up basically saying if it's a pristine gas falling in or get a plethora of astrophysical problems with very high redshift quasars, from the sub-milliparsec scales of the black holes to the tens of megaparsec scales of the reionization. Now we'll conclude with a summary of what I think are the big achievements of studying high redshift quasars and where we failed as a community. I think a big achievement was the measurement of the neutral fraction of gas at the epoch of reionization. This has been really amazing, and with the samples growing and growing, the data quality improving, we'll get better and better measurements along different line of sights. We did find companions and indication of overdensities on large scales. This is painful because observations are really demanding, but we are getting there. We might be able to see the gas feeding on the sources if the laminal failures that we map are really inflowing material from the IGM, but it's unclear if that's the origin or if it's something different. Characterizing the host galaxies has been very successful with ALMA and millimeter facilities in general. It has been extremely disappointing so far with HST, and there's big hopes for James Webb. And I think where we really failed is to understand the black hole formation. We pushed the limits a lot. We made life tougher and tougher for modelers, but still we don't have a clue on what is the origin of these seeds and their formation mechanism. And I leave you with that.
So thanks, Roberto, for this great review. Questions? Alessandro.
Hi, Roberto. Thank you. Very, very nice talk. I am intrigued by the amount of dust. Is there any indication that the amount of dust is not normal compared to the amount of gas?
No. So it's a very good point. A very good question. We find values of the dust-to-gas ratios that are in line with what you typically expect for local universe, for instance. One caveat that we need to keep in mind is that everything that we see, basically these wavelengths, is only looking at some metal-enriched gas, right? We are not talking about the completely pristine gas. That's very hard to probe. But basically, the gas we see is behaving as in the local universe in terms of dust-to-gas ratios and so on.
Other questions? Giovanni.
Ciao Roberto, do you have a comparison between how compact these hosts are with respect, for example, to sub-millimeter galaxies at lower redshift that are thought to be major remnants as well?
So that's a very good question. The sub-millimeter galaxy is a very mixed bag in the sense that there are some sources that are more extended, but typically associated with ongoing mergers of wet mergers with a lot of gas in both the galaxies. There are some studies where they see that the dust emission is really compact. I'm thinking of the Hodge 2016 or so papers that they found they did observation with ALMA at very high angular resolution, and they found that the dust is really compact. So it's possible that again there's probably this similar situation as the quasar, where the more extended sources are the one where you see the interaction still ongoing, and the more compact ones are past the interaction or before. But I don't have an answer on the dynamical states of these cases. maybe someone in the SMG community knows that. I don't.
There's the question from Nico.
There's more curiosity. The mass measurements for the black holes are redshift 6. I suppose they're calibrated from the local relations. How precise are they? Do you have an idea of the scatter they can have?
Yes, yeah, that's a very, very good point. So what we use is the magnesium line, which is a low ionization broad emission line, and it's as good as it gets as a proxy of the gas that you typically probe with H beta or H alpha in the local universe. There are cross calibrations with Sloan samples at redshift 1 and 2 to make sure that this sort of works, at least on a statistical base. All of these measurements to first order are not, the error bar is order of 0.3x that you get for free just because you don't know the orientation of the system, you don't know, you shouldn't trust a single black hole mass better than that value. That said, there are some points, like if the black hole is smaller than that, then you really have a problem to justify the luminosity. You take the luminosity, you assume it's Eddington accretion, you get you assume it's all Eddington, and you get a black hole mass that's order of 10 to the 9. So there's not so much wiggling room there.
Very last quick questions. Down there, Federico.
Very nice talk. Again, regarding the compactness of these sources, of course, the cosmical surface brightness dimming is very strong above redshift 6. So could it be that we are seeing only the nuclear regions of the galaxies and there could be more extended emission?
Excellent point.
I think we can move to the next speaker. Next speaker is Giada Bargiacchi, who will talk us about quasars at high redshift as cosmological probes.
So, hello everyone, and first I would like to thank the organizer for giving me the opportunity to give this talk, and also all of you for being here also after the football match and the social dinner, so thank you. I am Giada Bargiacchi, a second-year PhD student at the Scuola Superiore Meridionale in Naples in the Space PhD project. And my talk is titled Quasars as High Redshift Cosmological Probes. First, I just would like to briefly recap the XIV luminosity relation for quasars, but you already listened about this relation on Tuesday by Susanna Bisogni, and you would also listen later in this morning by Matilde Signorini. So I'll be very quick on this. And then I will focus on how we can use quasars as standardizable candles, and our recent results based on this paper here. On testing different kind of cosmological model using both the combined sample of quasars and supernovae, and in some cases a sample of baryonic acoustic oscillations. Just to start, as you know, the XIV luminosity relation for quasars has been known for a lot of time in the literature, parameterized this way as a linear relation between the logarithm of these physical quantities with this slope gamma and intercept beta. But until the recent year, this relation was characterized by a very high intrinsic dispersion, with a value of about 0.35, 0.40 in a logarithmic unit. So this didn't allow us to use this relation for cosmological application. But just in the last few years, my research group proved that this dispersion here is not completely intrinsic, but mainly due to observational issue. So selecting and cleaning the sample to remove all possible biases in both the X and UV band, we are able to build a final clean sample that is suitable for the cosmological application. Now we are using a sample that is composed of 2,421 sources in a redshift range up to redshift of about 7.5, with a very strongly reduced intrinsic dispersion with a value of about 0.2 in logarithmic unit. Just using this luminosity relation and converting to flux, we end up with this relation here, from which we can infer the luminosity distance of each quasars, just measuring the X and UV fluxes and knowing the value of gamma and beta. Here, I don't give you too many details, but I can say that we are able to measure these quantities, but most importantly, we proved that both gamma and beta do not evolve with redshift. That is crucial for the cosmological application of this relation here. So this relation allows us to use quasars as standardizable candles. So to include them in the Hubble diagram of supernovae. You have just seen this plot before. This is the relation between the distance moduli and the redshift. And here you have the magenta point that are the supernovae 1A and quasars that are divided by colors according to the subsample they belong to. And the black point, you will see in a while, are no matter, are the average for the distance moduli of quasars in redshift beams. We need, in this plot you were seeing before, the supernovae as calibrator for the Hubble diagram, because we need to fix the 0 point of this diagram. So in the low redshift range, just here. And as you can see, in the common redshift range, the Hubble diagram of supernovae completely overlap with the one of quasars, and this proves the reliability of our method. But the most crucial point here is that quasars allow us to extend the Hubble diagram in a redshift range, in the high redshift range, that is not covered by supernovae, and that is the one that we need for testing and comparing prediction of different cosmological models, and also for comparing this prediction with the observational data. So here I'm going to present you some of our results in testing different cosmological models on this combined sample of quasars and supernovae and a sample of baryonic acoustic oscillations. Just starting from the simplest flat lambda CDM model. Here on the right you can see the triangle plot obtained using the combined sample of quasars and supernovae, and we are marginalizing over all the free parameter of the quasar relation. And as we obtain consistent results from quasars and supernovae and BAO, we can just fit the combined sample. And we end up with an omega M0 that is 0.3. So completely in agreement with the expectation and with the latest cosmological evidence. But now, what happens if we instead test extension of this model? For example, just relaxing the assumption on the flatness of the universe. Well, in this case, you can see from this bidimensional contour plot that here we have the colored contour that are the 1 to 3 sigma confidence level for the two different probes. We end up with a completely strong inconsistency between the two probes at more than 3 sigma. Indeed, BAO favors a flatness universe. Indeed, this green line is the flatness condition, while quasars and supernovae favors strongly a closed universe. So in this case, due to this inconsistency, we cannot combine the two probes. This is the reason why we are not showing here the intersection. We also tested the flat, if it's working. Okay, okay. Un pochino prima e basta.
Riusciamo a espanderlo.
Vabbè, comunque è scritto abbastanza.
You can go with this. I'm sorry. I'm going to fix it later. Sorry.
No problem. I'm going just back in the slide. Okay, this one. Okay. Yeah, I was saying that we also tested a flat WCDM model in which the equation of state of dark energy is still constant, but in principle can be different from -1. That is the value assumed in the flat lambda CDM model. In this case, we recover the consistence between the two probes, so we can fit also the combined sample, and we obtain a 3 sigma discrepancy with respect to the prediction of the flat lambda CDM model, in the direction of an omega m0 that is greater than 0.3 and a W0 lower than -1. So a phantom dark energy scenario. Once again, relaxing the flatness assumption, if this could work. Okay. Okay. Here, once again, you can see that as for the non-flat lambda CDM model, once again, we end up with a strong inconsistency between the two probes in the same direction. I mean, always with BAO confirming almost a flat universe, while quasars and supernovae a closed one. We also tested other parameterization, the very well-known CPL1, in which the dark energy is evolving in time as a linear function of the scale factor A. And as you can see here, also thanks to the large uncertainty due to the higher number of degrees of freedom in this model, the probes are consistent. We can fit the combined sample, and once again, we end up with a 2-3 sigma discrepancy from the expectation of the flat lambda CDM model. Once again, with an omega m greater than 0.3, a W0 lower than -1, and a WA that is slightly positive. In the same framework, we also tested other evolving dark energy scenario, such as this parameterization here, the JBP, the Barpos-Alcanis, and the so-called exponential proposed in Young et al. 2019. As all these parameterization verify some physical and theoretical requirements, such as the fact that dark energy must be dominant only at low redshift and must be repulsive against the gravitational force to explain the present acceleration of the expansion of the universe. All these parameterization gave us, okay, can you? All this parameterization gave us common results also with respect to the one we have seen before, with a 2-3 sigma discrepancy for the combined sample with respect to the flat lambda CDM model, and with greater values of omega m0 and WA, and lower values for W0. So, just concluding, here we have seen that we are able, thanks to the XIV relation, to turn quasars into standardizable candles, and that under the assumption of the flat lambda CDM model, we recover exactly what we expect. But relaxing this assumption, then we end up with a strong discrepancy of 2-3 sigma with respect to the expectation, even if we can combine the probe only under the assumption of the flat universe. So we have seen that in the framework of a dark energy evolving scenario, we obtain an omega m greater than 0.3, a W0 lower than -1, and a WA slightly positive. And this particular behavior for a phantom dark energy is mainly driven by our sample of quasars and supernovae. And just to give you an idea, we are still working on some development of this work, mainly trying to shed shed light also on the physical origin of the XUV relation that is not still well understood, and develop the quasar sample both for in the number of sources and in the quality of measurement. And we are also testing other cosmological models, including the interacting dark energy ones, also including other important cosmological probes as the cosmic microwave background, dark energy survey, and gamma ray bars, for example. So I thank you for the attention, and I stop here.
Thank you. Questions for Giada? Maurizio.
So I know this is a question that goes way back to when the sample was assembled, but now that you have all these constraints, I was wondering if you can reverse the argument and wonder how, what systematics should be in the data to account for your discrepancy. So could there be, if there is a systematic, could be as large as you observe to reconcile completely, for instance, supernova and quasars with BAOs?
Okay, I didn't focus in this presentation on the way we build the sample, and it's a very long story, but just to be quick, we also in the last paper, Luce et al. 2020, we tried to cover and studied all possible biases and systematics, studying also possible correlations, and proving that our selection is safe from the point of view of biases and systematics.
Other questions down there in the back?
So very nice talk. I really enjoyed it. So basically, you have shown that you have done the fit to the data of quasars, and relaxing basically the assumption of flatness. For example, you have shown that you get also results very different from the standard cosmological model. Have you also tried to do some model comparison? Because clearly you are adding a parameter. I mean, I'm perfectly fine with this, but have you also tried to do some model comparison I don't know, like Bayesian information criterion, something like this, to see which model perform better or not? Thank you.
Thank you for the question. This is not part of this work here, but we are still working on development of this analysis using also Cosmo MC. And in this new work, we're also going to do some model comparison. It is, as you were saying, important to understand, we see discrepancy in all model, but which model is better with respect to the another one, and also with respect to the null hypothesis of the flat lambda CDM model. So we are going to do this also. Thanks.
I think we can move on. Thank you very much, Giada. So the next speaker is Roberta Tripodi from the University of Trieste, who will talk us about high-resolution gas and dust measurements in the first quasars. Ti avverto 2 o 3 minuti prima, cosa preferisci?
3. Sì, siamo tranquilli. O quindi 3 prima dei 12, giusto? Ok, perfetto. Grazie. Okay, thank you. I'm Roberta, PhD student at the University of Trieste, and today I'm going to present you my ongoing work about the high-resolution gas and dust of the first quasars. So, in the last few days, several speakers have highlighted the importance of study quasars at whole redshift, but especially at high redshift, they are of the most importance because, for instance, we could trace the history of formation of massive objects. And in particular, in my study, I will focus on the analysis of the cold gas and dust in these high redshift quasars. And with high redshift, I mean redshift higher than 6. And to do what? Basically, mainly to infer the properties of the cold gas and dust, but most of all to relate the properties of the supermassive black hole with the one of their own host galaxies. So, going straight to the point, initially we performed an extensive analysis of the quasar J2310 plus 1855 that is nearly at redshift 6. And what I present you in this slide are the results for the C+ and water vapor emission. And thanks to a long integration ALMA observation with high resolution and high sensitivity on this source, we could resolve the C+ emission, but most of all, we could finally study the kinematics and dynamics of C+, and in particular, we retrieved our best estimate for the dynamical mass through dynamical modeling using the software 3D Barolo by the editor Fraternali 2015, and the dynamical mass we obtain is of the order of 5 times 10 to the 10 solar masses. That is in agreement with the previous findings in the literature, but here the news is that we can resolve the disk. In fact, as you can see over there, I show you the velocity rotation and velocity dispersion profiles along the disk, and the gray area marks the region of the central beam. So we exclude that from the analysis. So you see here that the rotation curve is rather flat all over the disk. And with these two profiles, we were able to study also the Tumre parameter profiles, and we gained the information about the stability or instability of the disk. And what we can say here is that the disk is marginally stable because in average the Tumre parameter is about of the order of 3. And this work was also done for another high redshift quasar by Walter 2022, as De Carli showed before. And then we were lucky to detect the water vapor emission, and for the first time we resolved it thanks to the high resolution of this observation. And Pensabene talked a lot about the importance of studying water vapor emission, and in this particular case, comparing the water vapor luminosity with the total infrared luminosity of this quasar and putting it in a little bit of context, you see here that our quasar follow the main observational trend for high redshift quasars and also 1 sub-millimeter galaxy here, and also the relation found by Young 2013 for high redshift objects. And then, most importantly, we discover an outflow in C+, and there are very, very few cases at high redshift because they are very difficult to detect them. And in particular, you see here that there are these little excess here in the blue and red part of the emission with respect to the double Gaussian fit, and also in this PV diagram that is taken along the minor axis, and this in the map, basically these are the contours of the wings. The major axis is basically in the direction of the shift of the two peaks. You see that the model of Barolo, that is this dashed line here, doesn't take into account these two emissions that can be associated with the blue and the red wing. So we computed the mass outflow rate for the outflow in general, so take into account both the blue part and the red part, and we see that our values are in agreement with cosmological simulation, hydrodynamical simulation for high redshift object by Barai 2018, and computing a little bit of energetics, we see that this ratio here between the power of the outflow and the bolometric luminosity is a little bit low, and it is not in agreement with molecular winds, but more with ionized winds. And if you see here the residuals from the model of Barolo, so data minus model, basically, for the velocity map and the dispersion map, especially in the dispersion map, you see that there is some excess that Barolo cannot model, so we can guess that this excess is due to the outflow, basically. Oh no. Oh no. Okay. So then we focus on the analysis of the dust of the source. Why? Because we want to gain insights about the dust properties of this source, but most of all to compute the star formation rate so that we can compare the properties of the supermassive black hole that is the black hole growth efficiency, this ratio here, m dot black hole over m black hole, with the growth efficiency of the galaxy, that is basically the star formation rate efficiency, star formation rate over the dynamical mass. So we retrieved the dynamical mass before, and now we want to compute the star formation rate. Okay, so what we get for J2310, thanks to the very accurate sampling of the distribution, both with ALMA data and Herschel data, we compute with high precision between 5 and 10% uncertainties for the dust temperature, the dust mass, and so we compute the star formation rate. This is of the order of 1,000 solar masses per year. That is a little bit smaller than Shao 2019 because we account for the contribution of the quasars, as suggested in the paper of Duras 2017. And what I want to highlight here is that the ALMA point in band 8 and 9 are essential to finally precisely constrain the dust temperature, and so to retrieve a reliable value for the star formation rate. So let's see what we have for J2310. If we compare the black hole growth efficiency with the galaxy growth efficiency, we see here that the black hole is slightly slowing down its accretion of the order of the 50% with respect to the growth of the galaxy. And you can see here, this is our results in a bit of context of quasars at redshift greater than 2. You see that the slope of the arrow is taking into account the fact that the black hole is slowing down at one half with respect to the galaxy. And so basically we guess that our quasar is in this stage here when the feedback could slow down the accretion of the supermassive black hole. And one possible cause could be the AGN relatively driven winds, and in this quasar it has been seen ionized wind in carbon-4 bulk system, and Manuela will talk about it extensively tomorrow. So basically what we are saying here is that we are very probably witnessing the falling of the black hole dominance era for this quasar, clearly. Okay, then what we want to do next is to extend the same kind of analysis for a greater sample to access the properties of the whole population of high redshift quasars. And this sample is mainly drawn from the hyperluminous quasars at the epoch of reionization survey. And Luca Zappacosta will talk about that later today. What I want to say here is that among all the objectives that this survey wants to achieve, I will focus mainly on investigation of the nuclear and the host interstellar medium, as you can guess. Okay, so these are only preliminary results because this work is still in progress, but what I can tell you is that we computed for a subsample of the original Hyperion sample till now the dust temperature and the dust mass with the same procedure done for J2310, and comparing with other samples of quasars from D'Amato et al. 2020 at lower redshift, you see here that there is not a clear trend with redshift, and that also that the dust temperature is spread along 30 to 80 Kelvin, while the dust mass is always of the order 10 to the 8 solar masses, and the smallest error bar can be achieved because of the accurate sampling of the distribution. So if you have many data at all the observed frequency for ALMA, you can achieve this high precision, basically, both for the dust temperature and dust mass. And then, because we also focused on the analysis of the carbon monoxide transition for this quasar, we could compute the gas mass for this subsample, and getting the gas-to-dust ratio, you can see that there is a large variation in the range between 30 to 140. In literature, you usually see that the gas-to-dust ratio assumed is of the order of 100, so we are basically in agreement consistent with what's seen in the literature. And if we make a comparison with other quasars at the same redshift range and a redshift less than 6, you see that there is not a trend with the redshift of the gas-to-dust ratio. Maybe this answers a little bit for the question of Alessandro Marconi. And so this is, I leave here my conclusion. What I only want to stress, the take-home message, is what we can achieve using ALMA observation, and we find out the outflow. We could study the property of the supermassive black hole relating with the properties of the host galaxy. So the kind of information are very important, very essential to understand what is going on at the early stage of the galaxy evolution. So thank you very much.
Thank you, Roberta. Questions from the audience? Roberto?
Very nice talk. I was wondering for the water plot that you showed, the resolved map, do you see any evidence that the relation deviates from linearity? Because that's something we were wondering with Antonio for a lot.
Okay.
Here, yeah, thanks. Yeah.
Okay. The deviation, you see if this fit actually is taking into account the real behavior. Yeah, I think that this fit could be redone because maybe the trend is less. The slope is less, basically, of this curve. So I think that this one is a little bit old now. In fact, Young 2013 didn't have the point of Pensa-Bennett 2021 or Lerner 20 because, yeah, it was a really old prescription. So, yes, we can do maybe another study also of this.
Rita?
I think it's just a clarification. If you go back, if you can go to the next slide, slide 4, when you write that very few cases of outflow in quasar at high redshift, but we are seeing that the outflow cadence or the detection of outflows at high luminosities is higher than lower luminosity quasars. So I guess my question is there any relation between, so why these few cases of outflows in quasar at high redshift, if there is a luminosity trend on the detection of outflows, if this is true, or if you can make like a sort of connection between what we are seeing, for example, from the Piconcelli review on these high luminosities where the detection of outflows was much higher.
Okay.
I don't know if my question
these
was...
cases are the detection of outflows that could be like studied in detail, computed the mass outflow rate and a little bit of energetics. And the problem is that the presence of outflows is high in theory, but the point is that the outflows that can be like resolved or studied. Sorry.
It's just being at LOC and trying to do some scientific actually combination.
Yeah. For example, Bischetti 2019 actually detect the outflow only stacking different sources, but to detect a clearly seen outflow in one source is not so common. Maybe I can be wrong, but searching in the literature, doing this kind of precision study of the outflow is very difficult because the outflow are weak, and distinguish between the line that we are observing and the wings outflow could be very tough at some times. In fact, the signal to noise here is not higher.
Thanks, Roberta. Let's thank the speaker again. Now we move to Nico Capelluti from the University of Miami, who will talk us about primordial black holes.
Wait.
What's happening?
The PowerPoint has a problem with the content. I can read the file.
Can't read it.
You can't read it? I can make...
Says there's a corruption or something like that in the
So maybe we can switch.
I send you a PDF.
Yes.
Good.
So we can probably switch if Fabio is around. Yes. So next speaker is Fabio Fontanotte from INAF Trieste, and he will talk us about Eddington and creating black holes in the epoch of reionization.
Okay, good morning, everybody. So I didn't get the last slot before the coffee break, which is good. So, well, today. Oh. So which one? Okay. So I will discuss a little bit with you about the epoch of reionization. That's the aim of my talk, which is one of the main phase transitions that the universe has experienced, in particular the one that brings most of the baryonic gas from a neutral stage to a ionized stage. As most of you may probably already know, okay, it's very sensible, there has been a long-standing discussion about which are the sources responsible for ionization. I mean, the sources providing most of the ionizing photons. And to make a long story short, nowadays people are just discussing about AGNs and galaxies. And of course, this is a game with a lot of uncertainties, a lot of unknowns. Okay. And in particular, one of the biggest one is the so-called escape fraction. I mean, the fraction of ionized photons provided by a given source that are actually able to escape the galaxy or the AGN and impact the IgM medium and then provide reionization. Again, the comparison between active galactic nuclei and galaxies is mainly on the basis that there have been, well, AGNs are very efficient producers of ionizing photons, but there are quite a few of them. While there are a lot of galaxies around, especially star-forming galaxies at the IA universe, but they are not really efficient in producing ionizing photons. So, okay, just skipping and making a few spoilers. Well, we've been in the game for a long time, and actually I would like to stress that already 4 years ago in the previous edition of the AGN conferences, we had this model that was our favorite model at the time, and the idea was that you can actually reproduce the level of ionizing background required for ionization if you combine the contribution from AGNs and galaxies. And the key point was the fact that although AGNs were subdominant, this blue line, for example, is from the luminosity function by Hopkins et al., they could provide a decent contribution for the galaxies to close the gap with a relatively low escape fraction. So we were happy. So this is the talk and this is the end. Well, unfortunately, that's not the case. Things evolve quite faster in astrophysics, as many of you know. And, well, after a while, there have been a number of different works by other people trying to claim that the AGNs can provide a larger contribution. Especially there's been a work by Emanuele Gianlongo and Andrea Grazian. They revised essentially the faint end of the luminosity function of the AGNs at higher redshift. And the claim is that you can build up a large number, a large fraction of the ionizing background just with the AGNs alone, if you can just integrate up to very faint luminosities. Well, I know this is quite controversial. A lot of people doesn't believe this result. So I would just like to add a few more points to this. Well, first of all, let me just make a little bit of an advertisement about this Kubrick project that we are, trying to develop in Trieste. Most of the people listed here that belong to the project are actually based in Trieste, but there is a decent, a very important contribution also from collaborators from all over the world. Well, the idea beyond Kubrick's is trying to identify bright quasars in the southern sky by using already available public surveys like SkyMapper, Gaia, 2MASS, and WISE. Well, why in the southern sky? Because historically speaking, most of the AGN's luminosity function are based in the northern sky. For example, those based on the Sloan sky, on the Sloan data. Well, okay, I think I'll go on. Okay. The other important point in the Kubrick's exercise is the fact that we are applying machine learning algorithms in order to select reliable candidates. Well, of course, each of these algorithms requires talk by itself, so I just leave you. Okay. some highlights about and the reference for the paper if you want to read, if you want to go into this point. Well, for example, we use the so-called canonical correlation analysis and the probabilistic random forest. This is a work done by a PhD student, Francesco Guarnieri, at the University of Trieste. And the key point is the fact that this algorithm provides a large number or a huge list of QSO candidates. And we start, of course, when you have a candidate, you want to observe it and confirm it. And we actually started a spectroscopic campaign to recognize the best candidates. And we have more or less a 70% success rate, which I think is pretty good. Okay? And just let me flash through. Okay, well, this is a sky map. I don't want to spend much time there. Just let me flash through a few results that are relevant for what we are discussing here today. The estimate of the luminosity function. Let's start with this work by Konstantina Butze, 2021. She uses 58 new bright quasars that were discovered within Kubrick's. And combine this with other data coming from previous surveys, we are able to provide a new estimate for the luminosity function. That suggested some revision of the already available data upwards, okay? So this is systematically higher than previous estimate at redshift 4. Okay, this is telling us something. We are getting more quasars than we was expecting. If you move to redshift 5, it's even worse in the sense that Andrea Grazian provided this paper. Those are only 14 new ultra-bright quasars, so the magnitude range is relatively small. But again, the space density is higher than any other estimator at similar redshift. And again, Andrea is pushing the fact that if you just move the luminosity function estimated by Konstantina with the PDA, pure density evolution, you get to this point, and you're still higher than any other observation. So, well, I'm not claiming that, okay, well, perfectly on time. I wasn't expecting this. Well, it's difficult to claim from one point that the luminosity function has to be revised upwards, but it's pretty clear that we are getting more quasars in the south than previous people have done in the north, for example. Well, then this game prompted to some question like a revision of what we did in 2016. So in particular, we started asking the question, so if this luminosity, quite high luminosity function is real, could this quasar provide enough ionizing photons? Again, it's the same question, but starting from a different point. And in particular, in this case, we wanted to focus on the idea that if the guys lying on the luminosity function are all accreting at the Eddington limit for a decent fraction of their lifetime, how many ionizing photons would they provide? Okay, therefore, we built up this very simple toy model. Okay, this is, I mean, there is no n-body simulation or complicated stuff. It's just using the equation for the evolution of the black hole mass, starting from a seed mass. I will skip the parameters. And the main point here, the main parameter of the game is the so-called duty cycle. With duty cycle, we mean the time fraction that a given supermassive black hole spent accreting at the Eddington time. Okay, and using this rule, you can just predict the evolution of the supermassive black hole mass function. And given that you are assuming that those guys are accreting at the Eddington limit, this translates into a luminosity function, of course. And well, can I stop on the right slide? Okay, that's the point. And therefore, you can provide a prediction for the evolution of the luminosity function as a function of the duty cycle. And the duty cycle is the only parameter in this game that we are playing with. Okay. Let me also stress that in this scenario, the duty cycle also represents the probability that the given supermassive black hole is actually accreting. And this will be important in a few slides. Okay, so once you have a rule for evolving your luminosity function, you may try to, well, the key point is trying to constrain this value of the duty cycle by comparing with observations. And of course, you have a couple of observations you want to show. And the first one is, of course, the comparison with the background. And again, this is pretty standard math to a certain extent. We are just using the framework that Francesco Hart and Piero Madao did in 2012 to estimate the density of ionizing photons and the photoionization rates as a function of redshift. Of course, this critically depends on the depth in which you integrate your luminosity function. And let me just stress for, lack of time, on the deepest on the deepest integration. Like this is 0.01 L star at this redshift if you want. So by comparing these lines that represent the different values of the duty cycle, you may say that if you want AGNs to be the dominant producers, the dominant contributors to the background, you need a duty cycle which should be larger than, say, 20%, with a definite preference for 10%. Okay, so far so good. Well, that's not enough actually to get ionization. So fit in the background is not enough to, to get the ionization, because as Roberto showed just a few talks ago, you also need to reproduce the evolution of the hydrogen neutral fraction, okay, which is even tougher constraint in terms of ionization physics. And again, if you want to reproduce this with our simple models, well, only models which have a duty cycle very short, like 5%, are able to do the game. Okay, our preferred model, 10%, is light on the high side, and in particular, it's difficult to reproduce the Gam-Peterson data here below, which more or less tells you when ionization have to end, okay? So from this plot, I would say I would prefer 5% duty cycle. Well, that's not the end of the story, because as I told you, if I have a luminosity function, I also have, okay, a prediction for the evolution of the supermassive black hole mass function, okay, which again, it comes out to the fact that only a fraction of these guys are active in this framework. And here, the comparison is a bit more complicated because we do not have observation, but luckily enough, there are a number of models, and in particular here, I'm comparing with the model that Alessandro Trinca will discuss after the coffee break, if I remember correctly. And the idea here is a forward model starting from a heavy seeding scenario, and you try to predict the mass function at different redshifts. Here we are compared with our model, which is going backwards, okay? And the comparison tells you that this 5% line is actually in tension with this, this prediction for the evolution of the mass function. And here again, the numbers that you would prefer is between 20 and 10%, okay? So what we can conclude from this simple exercise, well, first of all, that if you want the AGN to be responsible for ionization, you have to go to a very small duty cycle, which translates into a very slow evolution of the luminosity function as well. Whereas if you, okay, and this is in tension with the model for the growth of the black holes from heavy seeds. Just spoiled the final slide. On the other end, models with 10% duty cycle are reproduced quite nicely the evolution of the ionizing background, if you integrate deep enough. Of course, this is always the thing. And okay, my time has ended, so I will just leave you with the last point. Of course, this is a very simplified toy model. I'm not saying this is the truth. And anyway, okay, the key point is really trying to constrain the evolution of the luminosity function, is normalization and shape evolution at high redshift. And the only thing to do that, well, you have to go through observation. So please stay tuned on our next releases for qubits QSOs, and let's see what happened for especially the faint end. And well, that's it.
Thanks, Fabio. Questions for Fabio? Annalisa.
Okay. Maybe I missed the point, but are you referring to the hydrogen ionization or helium?
Sure. No, hydrogen.
Hydrogen. It's a bit different, right?
Yeah, sure. Well, the point is helium ionization provides you another constraint on these models. There is also a lot of debate because, if the reionization by helium is homogeneous, you cannot simply do hydrogen ionization with QSOs because you would break those constraints. But if helium reionization is inhomogeneous, like recent observations seem to suggest, then you can fit the thing in the game.
Other questions? Beta. Oh, Fab. Okay. First, Beta. Fab.
Sorry, I will be quick. Just two quick questions. So one question is, when you compare the high luminosity points on the diagram when you show the previous results, like Kulkarni evolution. Can you go back? I think it's one of your luminosity functions. Yes.
4 or 5.
4 or 5. That's it. That's one. I guess, are you comparing pairs with pairs here? Because, for example, the Kulkarni relation here has been estimated from an analytical spectral energy distribution, which is an average of whatever AGN are at a given luminosities, while here you are just using 14 new ultra-bright quasars. So I'm just guessing, are you just simply testing the tip of the iceberg there, and that's why there is no...
Well, it's not a matter of the tip of the iceberg. Of course, I think Andrea did the plot, so it's not...
I'm just asking, I think it's a fair comparison.
I think the most interesting point is the comparison with the points, which represents data. Then there are the other models, which are reasonably based on the data. The point is we try to assess both for the incompleteness of our observations and for a reasonable volume correction. So,
exactly. Yes.
In principle, it's surprising that this data point is higher than all the other ones. I don't want to, well, some collaborator will start claiming that our selection is more complete than the other guys, especially with respect to the Sloan. That needs, in my opinion, more testing and more, science to be provided to convince the community. Well, the idea, I think we are going to the direction that we are more effective in selecting quasars candidates thanks to the machine learning algorithms, which are actually able to recover, well, I do not have the plot, unfortunately, if I can try. The point is you have to recover some quasars that lies very close to the stellar locus, which is impossible by using color cuts alone. And these algorithms are able to do that. And efficiently.
Well, this can be tested, actually. Fabio, quickly, last quick questions.
I agree with you. Actually, not even a question. It's just...
No, there was Fabio.
Sorry. I was wondering if you also have compared the luminosity function you found basically with redshift 6 luminosity function from like Matsuoka, the Shell Q surveys.
In my scheme, you mean?
No, in your work.
Okay, so it's a difficult, well, there are two answers. The first one, we didn't have any redshift 6 quasars from Kubrick's yet, so we didn't try. For my simplified model, I did, and you actually get another constraint on the duty cycle, which is of the order of 20% again. So with a 20% duty cycle, I'm able to reproduce the observed redshift 6 luminosity function. I don't have the plot, unfortunately. I can show you later if you want.
I think we can move to Nico, unless it's very urgent from Fabrizio. Okay, so let's thank Fabio again. So the last speaker before the coffee break is Nico Cappelluti from the University of Miami, talking about primordial black holes.
Okay. So if there is something that we can agree on in our research field is that one of the most intriguing questions of modern cosmology is, first of all, the nature of supermassive black holes, but also the nature of dark matter. So the LIGO and the recent detection through gravitational waves of black holes that do not fit in mass the classical electromagnetic counterparts, the classical electromagnetic scenario that we had before gravitational waves, in terms of being more massive, but in particular having a pre-merger spin, a pre-merger spin consistent with zero, and a post-merger spin larger than 1, meaning that the spin is acquired during the merger, points towards probably a different origin of these black holes. Also, there have been recent detection of about 60 long-duration microlensing events from OGLE. 20 of them have Gaia parallaxes, and so we have distance that lie within a few kiloparsecs. And this breaks the mass distance degeneracy microlensing and allows determination of masses. And these masses turns out to be of the order of 1 solar mass or so. But they are so close that if they would be stars, they would have been detected. So these masses overlap the stellar black hole mass gap and are consistent with the predicted primordial black hole mass distribution. Together with this, we have other interesting evidences that might fit the primordial black hole scenario, but I just want to give you an introduction, a very quick introduction of what we think are primordial black holes and how they form. So, in the first 2 seconds of the universe, the curvature is so high that basically everything is close to be a black hole, but it's not a black hole because they cannot collapse because of the very high sound speed. However, in the first 2 seconds of the universe, we have several phase transitions that during which you can demonstrate mostly at the QCD phase when you have the formation of quarks, pions, and these electrons, these subatomic particles. During this transition, you have a rapid drop of the sound speed, allowing the collapse of overdensity. So every time you have an overdensity that is crossing the horizon at this epoch, you can have collapses of regions of the size of the horizon. And since this happens at different stages, stage after stage, we have larger and larger horizon scales, so bigger and bigger black holes. So in this scenario, you have the formation of several types of primordial black holes from subsolar mass to intermediate mass black hole all the way up to 10 to the 6 solar masses. And there are several models, including the one that we're using, that actually allow to solve some problems that of our modern cosmology, like the dark matter baryon or the baryon photon ratio, or the so-called baryogenesis problem, that I'm not going into describing, but you can find it in this interesting paper from Bernard Carr. So, regardless of the nature of models, what we are using here, we are testing how our universe would look like if all the dark matter is made by primordial black hole with a broad mass spectrum. And here you see the distribution of primordial black hole masses. So where you see the mass of the black hole on the x-axis over the fraction of that matter as, for each mass. And you see that you can identify 4 peaks, one at low masses, one around the Chandrasekhar mass, which is the quark formation. Here is the pion formation at 10 to the 2 solar masses, and here you have the supermassive black hole seeds that are produced at the electron-positron epoch. And the mass density of this distribution is consistent also, these masses, with the mass density of intermediate mass black holes in the galactic center, or black holes of the mass of Sagittarius star. And here you see, and this part here is it's picking up, is basically the black holes that make the X-ray background. So how does a dark matter made of black holes influences the power spectrum of mass that actually leads to the formation of structures? So here it's, oops. Okay. So if dark matter is not made by particle, but by discrete structures like black holes, what you have is that basically dark matter is granular, and every time you have granular components in a power spectrum, we have a shock noise component. And here you see the lambda CDM power spectrum, and here is what you have when your typical mass in primordial black hole grows. So basically, there's a Poissonian component that is added to your power spectrum. So the net result is that you have a slight excess of power at very small scales, and this slight excess of power at very small scales leads you to earlier collapse of structures. And here you see, and for our model, this typical mass is 1.4 solar masses, because you have to average over the spectrum. So it's very tiny, but it's tiny enough that if you see the fraction of collapsed halos as a function of the redshift, compared with lambda CDM, which is in the dashed line, you see that at very low masses, the masses of so-called mini halos, the halos where we expect the formation of first stars, talking about a few thousand Kelvin in virial temperature, you see that you see an excess of halos at very high redshift. So having an excess of very high of very small halo at redshift might imply that you have an enhanced star formation early on in the universe. But this is not definitely true. It's not always true, because to form star, you need several ingredients. You need a potential well, you need baryons, and you have to make sure that baryons actually get into your halo. So we modeled our star formation rate using Press-Schechter with our new power spectrum. And with certain assumptions that come from the literature of the baryon conversion efficiency, the escape fraction, and so on and so forth. And on top of this, we added a component of accretion that onto this primordial black holes that comes from the fact that dark matter and baryons in the early universe have a relative velocity. And when you have black holes that are basically flying into the AGM, you can have, if the velocity are low enough, you can have Bondi-Hoyle-Littleton accretion, basically the accretion you have in high mass X-ray binaries. And you can demonstrate that this type of accretion ends up producing an ADAF model, an ADAF spectrum, and this might produce a significant component of the X-ray background. So results, so basically here is what we expect in terms of star formation rates compared with what we see. So here in different colors, you see different realization of our model, so basically varying FS, star formation efficiency, and so on and so forth. But basically you see that the evolution that we see is not very different from from the Maddow-Dickinson evolution high redshift. The only difference is that there are some models that predict a bumpier ride all the way up. So we might have episodes of higher star formation, but on average, if you look at the evolution of the Thomson optical depth, you end up having several scenarios that leads to the Planck results. But another thing is that we want to add quasars. And the very interesting results or feature of the PBH lambda CDM model is that if you want to compute how many black holes of a given mass you have in an halo of a given mass, so basically the HOD of your halos, this is basically proportional to your fraction of dark matter at a given mass times the ratio of the halo to and the black hole. So basically, if you bring this on the other side, you find that basically the M sigma or the M black hole, M halo relation is an intrinsic feature of our model. So we also, we basically, if you extrapolate these relations and applying SEDs, we can actually reproduce very well the redshift 6 E Rosita data. and extrapolations from Fabio Vito luminosity function. And another interesting feature is here you see the X-ray background that is produced by different components, X-ray binaries, PBHs, and QSO. Our model predicts that there will predicts no PBH, no quasar actually larger than 12. But since quasars forming the most massive halos as well, in principle we can actually extend this conclusion, given our assumption, to the lambda CDM model. So probably we don't expect to see any quasar redshift larger than 10 something. We also reproduce the unresolved cosmic infrared background, X-ray background cross fluctuations. And we predicted that since we have a higher number of small galaxies, JWST will be able to pick up an increase of the number counts near its flux limit. And skip this, and I want, if you allow me 30 seconds, I want to conclude this, this talk with a commercial. We are working hardly to propose for a NASA probe, AXIS, the Advanced X-ray Imaging Satellite, which is basically a version of Chandra with a constant PSF of 1 arcsecond across the field of view, 600 square centimeters at 1 keV, and many other interesting features. So the collaboration is now open to external collaborator. So if you want to join, please scan with your phone the QR code and register, and you can join our very interesting working groups. Thank you very much.
Thank you, Nico. Couple of quick questions. The first were in the back, and Federico. Federico? Or Luca? One from there.
Very nice talk, thank you. Even if including primordial black holes into cosmology means boosting the number of halos in which star formation is happening, how are you sure that an halo that is basically composed by black holes is not accreting the gas that is meant for star formation?
So in our model, we assume that since the circular velocity of the halos is high enough to switch off the bond accretion, that basically in the halos where star formation happens, you can only have quasars. But this is an assumption. You can have any other realization.
Federico and Fabrizio. It's okay.
Can I?
Yeah.
Okay. No, a curiosity, and if you know, who is supposed to provide the detector for AXIS?
MIT.
If I understand correctly, the excess of power on small scale would worsen a number of small-scale problems in lambda CDM, such as the missing satellites problem, the cusp versus core problem, and so on. Could you comment on this?
Well, this mostly happens in the high redshift universe because this component is not biased. So when you go when you have structures growing, the influence of this component will basically become negligible. So in fact, when you get at the redshift, let's say 6, when all these sources have already merged with halos, you end up having the same identical universe.
Okay. If there are no questions, there's an announcement from Beta.
Yes, so we're going to take the conference group photo just outside here. And so we're going to gather here before the coffee break. And I've collected, for those people that had attended the social dinner, I've collected all the receipts. So you can find them at the registration desk. You can collect them over there. Okay? So just take the group photo before we go to the coffee break.
So let's thank Nico.
Let's thank Nico.
I think we reconvene at 11 or 11 something.